Okay, well, let me just very quickly summarize what we talked about last time regarding the general optimization framework and a formal formulation. So we talked about the main technical difficulty of device poisoning attacks. I'll talk about it, basically requires solving a bi-level optimization problem. Also talked about how to solve it. The tradition wisdom says that gradient-based implicit differentiation can be used to solve it, basically replacing the inner optimization problem with a KKT condition. But it's very complex. The procedure is too complex to be applied to large-scale problems, including deep neural networks. So it is not suitable for deep neural networks. This paper basically proposed a back gradient optimization. Oh, okay. Well, I was gonna admit someone in the waiting room, but somehow disappeared. So let me make Kyle co-host so I can focus on the lecture. Okay, so this paper says that the contribution is provide some back gradient optimization so that it's more computationally efficient to device poisoning attacks. Okay, so we talked about attackers' knowledge. There is this perfect knowledge, which is not very practical, but is a worst case evaluation of the security of the learning algorithm. There is also the limited knowledge of attack, which is more realistic. Surrogate data scenario and a surrogate learners scenario, both are pretty common, as you can imagine, in practice. So the attacker's capability, this basically includes both the attacker influence and the data manipulation constraints. The attacker influence kind of divide attacks into poisoning and evasion attacks. And, because many of us are working on evasion attacks already, so I wanted to, spend the time talking about poisoning mainly for this lecture and probably for this class. And this data manipulation constraints actually applies both in poisoning and in evasion. But in evasion usually means that a perturbation that you can allow for a test example. So it's like a threat model power, right? The power of the threat model. Whereas in the poisoning, you would also have like insertion of a data or like deletion of a data or modification of a data and so on. Okay, so but for this paper, they have a more general characterization, which includes everything we're talking about, which is the so-called theta of the DC. So it's like a space of possible modification. So there is this attack strategy, which is basically an optimization problem if you think about it. But unfortunately, it is going to be a bi-level optimization. Of course, depending on the attacker's goal, whether it is an error generic poisoning attack or is an error specific poisoning attack, you can, for both scenarios, which are very different, but both scenarios finally converge to a bi-level optimization problem, right? With the outer loop being optimizing over the DC and the inner loop optimizing over the omega. So firstly, we talked about the gradient-based poisoning attack, and we also kind of wanted to talk about why it doesn't work for DNN. We said, through some careful manipulation of the gradients, we realized that, the gradient of the attacker with respect to this XC can be written as this form, right? But the difficulty here is that really it also depends on the W hat, which is learned from the learner. If you're imitating the learner, right, as an attacker. But the problem with that is that that double hat also depends on your XC, which is not optimized yet, which is your goal. Basically, you're trying to devise XC, the poisoning data point, right? So in order to do that, this is the challenge of the bi-level optimization problem. So basically reflected to the gradient, there is this term that you don't know how to solve, right? So how do we do that? Essentially, we're looking at a stationary condition and we're like replacing the inner optimization with the implicit function of taking the gradient equals to 0. But what's really interesting here is that you take an extra gradient with respect to XC, and that would actually give you a linear system, which will give you the solution of the previous quantity that we don't know how to solve, right? So but what this is saying is using the stationary condition, we will be able to find a closed form solution for that quantity in the previous slide here, okay? So that's the main idea. And essentially, finally, we see the gradient of the attacker's goal with respect to XC, which is how you would update your poisoning, is based on this formula here, right? It seems very complicated because it involves the Hessian matrix, an inverse of the Hessian matrix, as well as other complex quantities, including taking derivative with respect to omega, the parameter, as well as taking derivative with respect to XC. Okay. So, basically, last time we talked about the algorithm 1, we said, you have this iterative process where you update your omega hat by solving imitating a training problem. So you're solving like you train a learning algorithm basically, right? So once you do that based on your current estimation of XC, then you can use the projected gradient ascent to find the solution to find the update for the XC for next step, right? So, and then you do that again and again until convergence. Right? So as we also said before, the drawback really is that the computation and inverting the Hessian cost p cube time and p square memory, which is not practical for large networks, especially if you consider omega being the number of parameters in a narrow network, that would be just infeasible. So today we will be focusing on the poisoning with back gradient optimization, which is the contribution of this work. So I have a slide here, but it is a very condensed slide with a lot of information. Let's go one by one. So let's first look at here. So in order to basically solve the problem of like computation inefficiency, right? So they basically said, I don't want to solve the minimization, the inner minimization. What I do is I wanted to instead replace the inner optimization with a set of iteration. So it's like an incomplete solver of that minimization. So, just replace it with a set of iterations. The reason is, if you consider how you would solve the minimization problem, usually you would do something like gradient descent, right? Or some variance of gradient descent. But you would run until convergence. But here it is saying, I don't want it to run until convergence because it's too expensive. So the idea is very simple. I'll just run a few iterations, right? So a set of iterations performed by the learning algorithm to update the parameters. So in that sense, I'm not updating the parameter so that it's minimized, but I'm just updating it through some, local search algorithms such as gradient descent. Okay, so that's the first idea. So we're not going to solve that minimization problem. Let's go back to this algorithm here so that you know what I mean. So this one in the box here, right? So I'm using a set of iterations rather than solving the arg min problem. Okay, Now, second one is we're going to compute the desired gradient in the outer problem using the parameters omega t. So what is omega t? Before we got this omega hat from the argmin, right? Now this omega t is after you do t step of something like gradient descent, right? So obtained from an incomplete optimization of the inner problem after t iterations. Of course, apparently they're using t to denote the number of iterations you use in this incomplete optimization. Now, after that, so a naive thing that people can think of is you're going to just exploit this reverse mode differentiation, so-called backpropagation, to compute the gradient of the outer objective, right? So naive thing to do is just to store the entire set of parameters. So throughout the trajectory of the t steps, so it's W1 all the way up to WT. So sorry, omega, I mean to say omega, both, everything I have here, there's no W, there is only omega, which is denoting the parameter of the network, okay? So, you're just storing the whole set of parameter updates, omega 1 through omega t, and the forward derivatives, okay? So this is actually very memory demanding. I'll just pause a little bit here so that people understand what's going on here. Actually, in next slide, I'll have like a more detailed description of this, but first let's just digest this through a high level perspective. All right, so what this paper says is that this is, very memory demanding. Let's not do that. Let's do something smarter. Essentially, it's like trading some more compute. So you wanted to save some memory through a little bit more overhead on the computation. So of course there is no free lunch, right? You cannot achieve both, but because the memory, because sometimes it is too memory demanding, because each WI would require storing an entire neural network parameter, which is really expensive. So they kind of, solve this through computing WT backwards to W1 in reverse order with respect to the forward step in the backward pass. So that's a very good question. So Michael, do you want to explain the MAML? Everyone can see the chat, right? So Michael is asking what are the major differences between the technique and the meta learning approach like MAML?
Yeah, so I don't have a super great understanding of it, but you're trying to pick some initial parameters that will be good after a few steps of gradient descent. And so you do the steps of gradient descent and backprop through them. Sounds similar to this.
Mm-hmm. Sounds very similar. Anyone has more insight? Indeed, this back gradient optimization technique is not first introduced by this paper. It is introduced, I think, by a few other papers, if you read the paper earlier. Any other thoughts? Anyone working on meta learning wanted to comment on this? So I have a question for you, Michael. Do they also worry about memory? What I mean is, what are they doing? Are they doing the naive backpropagation or they're doing the smarter one?
I think they present the naive version, and then there's some sort of bad first order approximation that they use. I haven't heard of this smarter approach before.
Okay, great. So let's see. Let's move forward. I just wanted to give everyone put the gradient descent in here. So just for a recall, this is not related to the back gradient methods, right? So here we're talking about back gradient optimization, but we're talking about it because with that the gradient-based methods is not feasible. it's not scalable for neural nets. So let me put, the recall here. Before we're saying we wanted to compute the gradient of the objective function with respect to the poisoning data set through this equation, right? Through this update rule. It's not basically scalable, right? So I also wanted to put algorithm 1 here. This is we've already seen it before. But if you consider running algorithm 1 using gradient descent, then it's basically this step here, what I'm pointing at using my cursor. So it's this step, you're just going to replace this gradient with this equation here. Okay, everyone can see my cursor, right? Hopefully, because last few times you all confirmed that you can, so I would assume that you can still. Yeah,
we can see it.
Okay, wonderful. Great. So now, a naive way of doing that, the naive back gradient optimization, you consider instead of solving this what's in the blue box, right? You wanted to actually use some kind of T-step update. So the naive one would be algorithm 2. Consider that. So what would algorithm 2 do? It would actually just, instead of solving the argmin, but just run the gradient descent for T times. Okay, so it's very, very naive. I guess naive in some sense, but yeah. Any questions? So this algorithm is easy to understand, right? It is nothing but calculating gradient and then do gradient descent. So this is rather easy. And essentially, your W hat would be just the WT here, right? And then when you calculate these kind of things, you're going to still use this quantity here. Okay, so now the so-called, the smarter way of doing this is to kind of save memory, but through some kind of, so you don't store like W1 through WT and then do backpropagation. What you do is you kind of do it, you kind of reverse engineer it. Let's put it that way. Kind of reverse engineering it. How do you do that? Basically, this is on algorithm 3, right? So in algorithm 3, what you're doing will, this gradient update step will be through this algorithm 3 here instead of using that. So let's see how we're doing. As you can see, so basically, what I wanted to say here, we kind of leverage the back gradient descent to compute this derivative, right? In algorithm 3 by reversing a standard gradient descent procedure. Of course, with some fixed step size, for running, if you don't have a fixed step size, then you probably cannot reverse engineer it. For truncated training of the learning algorithm to T iterations, right? So you can see, as I said on the slide here, line 2 to 3 in algorithm 3 can be efficiently computed with Hessian vector product, as discussed before. And we also exploit the algorithm to compute the gradient of the attacker's objective with respect to XC in line 4 of our poisoning attack, right? So this is line 4 of the algorithm 1. And line 3 of the algorithm 1 is actually replaced with the incomplete optimization of the learning algorithm. So it's truncated to the T iterations. Okay, so now let's see what's going on. You can see instead of doing forward, it is actually doing things backwards, right? So it's T from capital T to 1. This is what's going on. First, you update the DXC, okay? So you updated the DXC through this quantity here. What is this quantity? Anyone wanted to see why do we do that? Why do we do that? Can you, yeah, take a look at this here, right? So because the gradient, so finally what you will get is this thing here, down here. But if you look at the equation, it has two parts. The first part is not directly related to the gradient of the omega. So it doesn't depend on, I mean, it is just depending on the previous value of omega, but not dependent on like, you know, specifically on the variations of omega. So in the first part is fine. So that's why here you just have this term copied. Now the second term depends on the omega, right? So this DXC is essentially trying to get this part of the update. See? Do you see that DXC is gonna be replaced, is gonna be used here. However, this DXC is calculated through T iterations. You can see, you know, from time capital T to time 1, reverse order, it will be updated through this. Okay, so this is corresponding to the second term. Now, because the omega is being updated, so that's why we need these terms. So these three lines, line 3, 4, 5, to update the omegas. So, or to reverse engineer the omegas, how would you do that? Right, so of course you have a fixed learning rate here, so you always have the eta. That's why you can reverse engineer them. So now what you do is you first, you know, take this step at line 3. Why do we do that? Why do we take this step at line 3? Someone remind, maybe you can refer to the previous slides. So let's first see. The d omega is nothing but only related to this d omega here, right? So for these two lines, it is not related to the d omega at all. Okay, so now this is backwards. So if you wanted to think of it, you know, forward, so you would first do this part, then do this part. First do line 3 and then do line 2, if you're not doing backwards, right? So now what happens is essentially you wanted to compute this term here. Do you see? So you are basically, you know, calculating the gradient with respect to DC, with respect to XC through these terms, but this term also depends on that. Okay. Does that make sense?
Yeah, so here DXA comes first because we are doing a back gradient descent.
Mm-hmm.
And because in the very upper formula there, the gradient respect to XC comes first. So actually in here, in the back gradient scheme, we put it in front of the gradient of W, right?
I'm not sure I follow your, is that a question?
Yeah, I'm just want to make sure that in algorithm 3, line 2 comes first because it's basically in a back gradient scheme, and according to the
You're looking at algorithm 2 now?
algorithm 3.
Oh, algorithm 3. Okay.
So
yeah, so T from capital T to 1.
Yeah, so I'm just understanding. I'm understanding that the derivative GXC comes first because it's in the backward scheme, back gradient descent, right?
True. Right. So basically, if you wanted to do everything in the forward,
we should do the DW first.
we should do DW, d omega first.
Okay.
Right.
Got it.
Okay. So of course, the details require a little bit of digestion, but really what I wanted to say here, which is the takeaway message, is that you just reverse engineer these gradients. Okay, so you don't have to store all the omegas. You somehow use the last one to reverse engineer to find the previous ones, and you can compute that. So, but however, the bad thing about it is that you would spend more computation, right? So, you have to compute, the previous omegas along the trajectory from time 1 to time t. So let's see, Michael has a question to check understanding. Will the sequence of omega t minus 1 in algorithm 3 end up recovering the same value of omega computed in algorithm 2? I think so. Yeah, that's what I would think. I don't see a reason why it won't. I mean, if the learning rate is really the same. But if you have some kind of adaptive learning rate, then I'm not quite sure, because sometimes if you do reverse engineering, you might lose track of the learning rate somehow if you do that in the normal order. Okay, so the drawback is really you have to compute these gradients, but the computation is not too bad. Basically, the time complexity is just linear in terms of the number of iterations. So you save some memory, but you have to make a compromise in terms of computation complexity. So you have an additional cost of OT time complexity here. Okay. All right. So that's all I wanted to say about defense. I mean, sorry, that's all I wanted to say about attack, poisoning attack. So I started, just to recall, I started with something that's more like motivating, right? So we see like how you can use some collision attack to successfully attack a neural network by freezing the feature representation layers. However, later on, we started with a formal formulation, and we learned that by level optimization. We learned how to do a back gradient optimization, and even better, we learned how to do it in a smart way so that we can save memory and with some little cost, which is manageable in terms of computation. So this is like an overview of the attacks. But like I said at the beginning of our lecture introducing poisoning, the reason why we study attack is really to defend against them, right? So wanted to study our enemy in order to defeat them better. So the whole idea why we introduce all the formal frameworks of the attacks is for this defense, poisoning defense. So today I will introduce this paper, Certified Defense for Data Poisoning Attacks. So I have the archive number here. Yeah, you should be able to find it online. So this is actually a framework that defends by remove outliers residing outside of a feasible stat. We'll talk about that. What's a feasible stat? And then minimize a margin-based loss on the remaining data. Okay, so it generates approximate upper bounds on the efficiency of any data poisoning attack under two assumptions. So I will also explain why they have these two assumptions, and possibly we can brainstorm how these assumptions could be avoided, or if these assumptions don't apply, what would that imply in terms of the theory we see? Okay, so the two assumptions are the empirical train and test distribution are close together, which is, I guess, reasonable, right? That's usually what we would assume. And the outlier removal does not significantly change the distribution of the clean data. So this is also, I guess, kind of realistic if you assume that your outlier removal doesn't remove a lot of examples, and you do have a lot of examples in your training data set. So of course, I think this doesn't apply to when the poisoning is very powerful. You can just have like 50% of the training examples that are poisoned. So I would think that if that's the scenario, then it's probably very hard to defend against those poisoning. So, but this paper still provides a very interesting view of like a certified defense for data poisoning attack. It's very different from certified defense for evasion attacks, like adversarial examples, right? And that's the reason why I wanted to introduce this in the lecture. Okay, so first I want to say they assume a causative attack model. What does that mean? It basically means that a causatic, the causatic attack model would just allow the attacker to add points, but not modify existing ones. Actually, I think the authors kind of justify that this is reasonable because the systems constantly collect new data, and modification of existing data would require some kind of compromising of the system, which is usually not very easy, right? But when you collect new data, then it's probably very easy that you get a poisoned example. So that's what they were trying to justify. For example, if you're collecting like product reviews, they could give you new reviews and something like that. So that's the causatic attack model. You can add points but not modify them. It is a little bit different from our perspective of like perturbing the images, but let's see what's going on here. But this slide, what I'm trying to say is that this paper is trying to come up with like a certified defense for poisoning. So it is actually framing this entire thing as a game between the defense and attack. So the defense seeks to learn a model, right? And this, they were not using omega, they were using theta here. So we have to switch our notation a little bit. So now the theta is the model. Of course, the defense wanted to have a low loss, right? So you wanted to get your training loss to be low. And that's what every defense mechanism is trying to do. And of course, the defense is also aware of the attack. So you wanted, basically not only they wanted to train the model that is have a low loss, but they would also, if they're smart enough, they would also consider the model would also have a low loss if there is an attack, right? So what the attacker is trying to do is they want the learner to learn a bad model, right? For example, a high loss. But of course, like we learned last time, it could be a targeted attack. So not necessarily a high loss, but some kind of bad performance for a specific class of images or something like that, right? So it's targeted. Also here, this paper has a very interesting assumption, which is, the attacker has full knowledge of a defender's algorithm. And also the attacker has full knowledge of the clean training data, DC. So we'll talk about that soon. But this seems to be very generous to the attacker, but the authors kind of justify that it is widely considered poor practice to rely on accuracy or like security, right? So you cannot assume that your data is secret or secure. It might just be exposed. So that's the incentive that they wanted to understand. Even for a very powerful attack, can we get a certified defense? And indeed, this is, I think it's very reasonable because anyway, you're talking about a worst case scenario. So, if you don't consider this exposure of your learning algorithm, exposure of your data, then you probably are not really talking about a worst case scenario. So in this paper, they're talking about a full knowledge. We talked about the attacker's knowledge, right, in the previous paper. But this one is the full knowledge. Okay, any questions? So how does the game work? The game works as the following. So you have an original training data, right? So that drawing from, you have data drawn from some underlying distribution that's unknown, right? P star, this is the underlying distribution. And, therefore you get a clean training data set DC, okay? So now this is based on the DC, the attacker is going to design a data set. So this is very important, is epsilon multiplied with n. So the original number of examples in your training data set is n. Of course, it's different. Again, this paper doesn't use small m, which is what we're used to when we're learning about learning theory. But this is using small n to denote the number of examples in your training data set. But now this is saying I'm using a fraction. I can poison, a data set of epsilon and points. So epsilon could potentially be much smaller than 1, right? Poison data set. So that's going to be denoted as DP, right? So C denotes for clean and P denotes for poisoned, where epsilon parameterizes the attacker's resources or attacker's power. Okay. And like I said, this is not a modification, but this is just inserting new points. Hopefully that's, clear enough. All right. So the attacker has full knowledge of the defender's algorithm and the training data, as we said before. Now, based on the attacker, what the defender wants to do? The defender is going to train the full data set, right? So the defender doesn't know DC or DP, but it only has like the full data set D, which is the union of DC and DP, right? So based on that, it's gonna train a model, theta hat, and a test loss, L of theta hat, is incurred during test time. Okay, so this is the entire process. Also, one thing I wanted to mention is that this paper is not focused on the attacker wanting to do a targeted attack. They are actually doing, they call it a denial of service attack, which is basically they just wanted to have an error generic attack. You just wanted to make sure the loss is very high. Okay, so if you look at, sometimes if you see a terminology of denial of service, then it just means that you wanted to maximize the loss. It's a non-targeted attack. Okay. Questions? No? Okay. So now the defense mechanism, well, basically, we need to talk about the defense mechanism, because a defender, if you're just naively training the full data set, DC union DP, then it's basically doomed to failure. Why? Because even as a single poison, poison data point can, in some cases, arbitrarily damage the model or change the model. This is actually proven in previous papers. If you look at that, actually, some papers from 2016, 2017, people have seen that. So that's why defense mechanism is so crucial, right? So here, we first wanted to introduce this data sanitizing defense. So its idea very simple. What you do is you wanted to examine the full data set and try to remove the poison points. Right? This is especially relevant because you're looking at a quantitative model, right? So you can only add points, but you cannot modify points. So wanted to pick out the points that are actually poisoned by removed, and then you remove them. Okay. So the idea is very simple. Data sanitization is very simple, but formally, it's just that the defender construct a feasible set. So now the feasible set is very, very important. So it would construct a feasible set and trains only on points in feasible set. So basically what we mean is that if your defense mechanism find a feasible set, then you would look at all the training examples, including the poison and the clean, and see whether the examples are in the feasible set. Okay, so that's why mathematically it's written here as argument of the losses of the theta and DC union DP, but they have to all be within the feasible set F. Okay. Any questions? So one thing you might think of is that, let's see, so if the feasible set is, of course, I haven't talked about how to construct a feasible set yet, right? So there are many ways of doing that. But let's say you have some feasible set, which is, designed by some defense mechanism. Is it possible that the feasible set is so narrow and so strict that even the clean data would not satisfy the feasibility? It's possible, right? So that's one concern here. And now, of course, if your feasible set is very relaxed, and even the poison data sets could get away with that, right? So they could still get into a training data set, and because they would satisfy the feasible set condition. Right. So think about these two extreme cases. And that's why, designing such a feasible set is so crucial. All right. So now, given such a defense feasible set, the upper bound, the worst possible test loss over any attacker is kind of interesting for us to understand the behavior of, or the performance of this feasible set. Now, you can also call this a defense because, this is basically a defender is going to use the feasible set to defend. Okay. So very importantly, this is a certified defense. So your upper bound, the worst possible test loss over any attacker. So also notice that this is a test loss, right? Over any attacker, so any choice of the DP. That's why it's a maximization of the DP of L theta hat, right? Theta hat is just the argument of this quantity, which is including DC and DP, but for all of them fall within the feasible set. Okay.
I have a question here.
Yeah.
So does this basically mean that the algorithm F you use to find the feasible set is actually independent with the noise poison data?
That's a very good point. So we have two scenarios. If F is independent, then it's called a fixed defense. But if F is dependent on the poison, then it's called an adaptive one. We will talk about that in the next few slides.
Okay, sure, thanks.
No problem. Any other questions?
I have a question. So
Sure.
Here, when we are upper bounding the worst possible test loss, basically we are for calculating the loss, I'll be looking at data points in my defense set F, right?
Defense set F? What? Sorry.
So how is this loss calculated? I mean, for calculating the loss, I don't know what DP is, right? I have the union set, but I don't know specifically what data points are in my poison data, right?
Exactly. And
So
that's why it's very difficult, right? You're getting an upper bound of the worst possible test loss over any attacker. So basically, for maximum of DP, you don't know, right? But you wanted to find it out. That's why it's very powerful.
so I want to find it out using this union set or the F set.
We'll talk about it soon in the next few slides.
Okay.
I haven't talked about the defense yet. Yeah.
Okay.
I'm just laying out the problem here, just
Mhm.
setting the stage, kind of telling us, what do we want it to do? What's the goal?
Okay.
Yeah. Okay. Other questions? Great questions. Okay, I can move forward, if I may. All right, so the defense mechanism, the data sanitization one, everything boils down to designing the feasible stat app, right? This is basically your defense mechanism or the defense algorithm, let's say. So like Chen Chen was saying, there are two ways of designing the app. So there is this fixed defense and there is this data dependent defense. I will call it adaptive defense. So the fixed defense is just the F does not depend on the poison, DP. Okay, so you're not aware of the DP. So, what do we mean by that? Basically, you just don't, because in practice, you don't know what's DP and what's DC. So basically, it's just data independent, kind of. So for example, if you consider in text classification, the F is just the document contains some kind of licensed words. So there, you've designed an F in a way that is independent of the training examples, right? The training documents you have. So that's a very good example of the fixed defense. So the paper also talk about special case, like Oracle defenders that depend on the true distribution, although, oftentimes this is not implementable, right? Okay. So of course, I haven't talked about F at all yet, but I'm just trying to, analyze how we can design such an F and what are the properties of the F and so on. Okay. So we have the fixed defense. Now I wanted to talk about the data dependent defense, and apparently it seems to be a more powerful one, right? Intuitively. So what do we do? The F depends on the poison, DP and union DC. Why? I cannot distinguish DP or DC. If I can, I might as well just remove the DP, right? So I can only rely on everything I observe. I don't know which one are poison, which one are clean. But nonetheless, I'm going to use my training data, poison training data, I would say, to design my F. So what basically this is doing, usually, this would involve like estimating P hat, the underlying ground truth, data distribution from the union of the poison and the clean data. Okay, so something related to that, although I'm just being very vague here, but the whole idea is that we don't want to specify it. We wanted to have more general framework first. Okay, so the data dependent defenses usually would wanted to do something like estimating the underlying distribution using the poison data. But one thing that we need to understand is that then, because you have such kind of data poison defense, the attacker can adapt as well, right? So if you are if you are designing your F based on the data, then I could try to choose my poison data to change the feasible stat F, right? In a way that is, playing against you. Do you see? So, then this becomes like an adaptive mechanism, right? It's like a competition between the attacker and the defender. Okay. So again, we're not talking about anything, very specific yet. I'm just talking about the framework, talking about, what are the interesting or no important concepts for us to understand the later contents. Okay, hopefully this is still very easy to understand. Now the attacker objective. So this is a very important slide. So for any theta, for any algorithm, I'm sorry, for any model theta, notice that now we've used theta to denote the model, not omega. So theta, for any theta, you have equation here, what I'm showing. So first of all, this I here, the approximation I here could potentially be invalid if you have overfitting, right? And now you can recall why this is saying that, when we first introduced the paper, they have these two assumptions, right? One assumption is that, the distribution of the training and test is very similar. So basically that means no overfitting, right? So this inequality only holds when there's no overfitting, okay? Or the generalization error gap is small. Okay, so that's the first inequality. If there is overfitting, then if we regularize the model appropriately, then we can show that the training and the test are close by some kind of like standard concentration argument or something, right? So now let's look at the second inequality here. So smaller than equal to this quantity. Why? This is only because you always have a non-negative loss function. So as I said, in this causative attack scenario, you can only inject new examples. You cannot modify. So that's why the original loss, right? So you can see this is the loss on these n examples. So if you inject the poison, then the loss would be greater. Strictly, of course, not strictly. If it is strictly greater, then you still have some loss on the poison, but it's going to be greater than equal to, right? Of course, this can be relatively tight as long as the model ends up actually, fitting the poison data very well. Okay. So now I'm also going to look at these equations. These are very important. So if we look at the maximization, right, the reason why we're looking at this, as I said in the previous slides, that this is the quantity we're interested in, right? How do we characterize it without knowing dp? So this is how we characterize it, right? So we have a maximization of this loss function theta hat. Again, if you follow inequality 1, which is, no overfitting, then you would have this guy, right? Approximation. But, they were hopefully very close to each other. Of course, you can also use some concentration inequality to bound this, but, this paper only talks about an approximation here. So once you have that, also, you would have this quantity. As we already said in the previous one, this 2 is just non-negative loss function you use here. So of course, this would hold because you just added this term here. So this dp union f. Now this is actually very interesting. You wanted to see, I have my DC, now that my DC is still here, but I have this term, dp union f. So now people might be very curious, what is going on here? If you have a feasible set, right? So a practical algorithm cannot just do a union of dp, sorry, not union, dp, intersect with like f. Why? Because you don't know dp, right? All you know is the union of dc and dp. So a practical algorithm would do something like this. Oh, what happened? So a practical algorithm would do something like, right? Do people agree? Oh, somehow it disappeared. Anyway, do people agree that?
Here, shouldn't it be DC union DP intersection
Yeah, I'm gonna, oh,
DC
okay.
union F.
Yeah, I mean, so do people agree this is what we can do in practice? Yes? Wish to see more yes? Okay, I'm seeing a lot of thumbs up. Great. Awesome. So now, of course, there is a discrepancy here. Okay, so now this goes back to the assumption 2 in this paper. Remember, what is the second assumption? Second assumption saying that you're actually not removing a lot of points in DC. Oh, sorry. I think why you are confused. This is I'm writing U here. I don't know what's going on, but this is DC union DP. Sorry about that. That's why you are confused. Now, does this make sense? So the assumption 2 in this paper previously said that you are assuming that this F, this feasible set F, does not remove a lot of DC. Okay, so now if that's the scenario, then this is very similar to this guy, right? Agree? Right. I see some, thumbs up also, but, feel free to ask a question if that's unclear.
I'm a bit confused here. So, is this DC union intersection of these two? If this is, if this is the case, then if we are opening it over the union, then shouldn't it be intersection DC union F?
Oh, no. So, so as a defender, what do you see? You don't see DC, right? Instead, you see DC union DP, right? That's what you see as a defender, right? This is going to be your poisoned training data set.
Mm-hmm.
So that's why, you would look at all the examples and check if it was in my feasible set. So that's why it is this term.
Okay. And one more thing, the middle term here, which is only considering DC, this does not.
Which one do you refer to?
The first.
We have the markers for each of the inequality. Which one are you? One. Okay.
Yeah.
Okay. Here.
Yeah. So here, this term does not depend on DP, right?
No, this term. Is that true? This term does not depend on DP. No, this term does not depend on DP. Yeah, true. Because we don't have the DP here.
Right. So maximizing over DP is.
However, no. So one thing is, however, the theta hat depend on the DP.
Okay.
Right. So so remember from the previous slides, your theta hat is something like, arc. So some kind of optimization. I don't know if arc min or arc max, but you know what I mean, like this. So let me go back to that then. Okay. So here, what I'm trying to say here is your theta hat depends on the DP.
Mm-hmm. Yeah.
Right.
Thank you.
Clear? No problem. Okay. Let's go back here. So, okay, so I don't think I need those notes. Let me get rid of them. Okay, so now, now we understand these two assumptions in this paper. Okay, so now let's look at 3. Okay, so for the final approximation, we have to go through 3 here. Okay, 3. So, okay, let's see. So we have the defender trained on DC union, the DP intersection with F. So basically, it means that it uses the entire training data set rather than just the you know, rather than just the training data set that has to fall into F, right? So this is actually something that is not very practical, but somehow this is the assumption that, you know, that this paper is making. So hopefully this does not have a large effect as long as the defense is not too aggressive. So, you know, also from here, we kind of denote it as theta tilde here. So here, theta tilde, just to show the difference, you know, because we want to make sure, how should I say this? I don't know why I don't have an eraser. Okay, so for this one here, this is not the normal thing we would do. So there is a discrepancy between how you would train your theta, because what you would really do is something like this, but you're doing something like this, right? So that's why the paper started to use theta tilde instead of theta hat. Okay, so putting it all together, the worst case test loss from any attacker DP was epsilon n elements is approximated upper bound as the sky, M here. So the last equation. So intuitively, the attacker achieves M is trying to maximize the loss on the full data set by adding poisoned points from the feasible set. So this is a very important claim. I'm saying that the attacker achieves M by trying to maximize loss on the full data set by adding poison points from the feasible set. So as you can see here, why I say that is that this DP has to be within the F. Okay. All right. So you're getting a maximization over the DP, but your maximization is over the minimization of the theta here. Why? Because that's how your training, your defense algorithm is trying to do. And that's why this becomes an upper bound of the performance, even under the worst scenario. Okay, I hope this is clear. Is that clear? Okay, so I'm gonna move forward. The theta hat is attacker's estimation. Okay, so we finally wanted to do that. So like we said, we have two ways of defense, right? So the data sanitization has the fixed defense and the data dependent one. Let's first look at the fixed one, because that's something that's easier to understand because it's not adaptive. So in the fixed one, it is actually quite simple, right? The F does not depend on the poison DP, right? We already gave you a few examples why it doesn't have to, because you could just design your rules for your F. So it doesn't have to be related to your data set. So I'm just recalling the equation here, right? So your M is just the upper bound of the maximization of the loss over DP. And now this is just the maximization of DP within F and minimization of the theta. Theta is the model parameters, and doing this 1 over n loss over theta DC union DP. Okay, so this is just a recall of the previous equation. So you know, the paper actually talks about the no regret online learning. So produce candidate attack again between the learner and the nature. So theta is just a tuple of radius rho. So if that's the scenario, let's see. So to derive the algorithm, actually we'll see the algorithm, but we simply swap the minimization and the maximization on 4. So the 4 just means the equation above, right? So you're trying to get an upper bound of M. How do you do that? So you first get this step. So again, let me try to use my, so this step, how do you get it? You're from here to here. So how do you get it? Why is it smaller than equal to? This is actually related to the max min inequality. Okay, so I know I know some of us was a little bit confused about this, but this is, if you look at the wiki page, actually I put the wiki page here. I'm gonna update the slides later on so you would see the wiki, but even if you just search for max mean inequality, you would see this and with a very simple proof on wiki page. Okay, so so this is basically you swap the min and max and you're getting an upper bound of the max min. Okay, so you get upper bound using that. Then now it's easy. So you can just denote your U as something related to that. And actually what they are doing is defining this term here. That's very easy, right? Why? Because my U theta is basically the sky. Now I have a part that is not related to my dp, so this is just that. But I do have another part that is related to DC, which I have to do a maximization because I have a worst case scenario, right? So that's why I maximize over the points within my feasible set. And can someone tell me why there is a single point? So think about it. I have epsilon n such points that I'm allowed to inject. But this is saying that for all of them, it is going to be just one data point, x, y, that maximize the loss. Do you agree? And if not, then what do you think is more reasonable way to do? And that's reasonable, right? Because if you wanted to find the points within a feasible set, of course you wanted to maximize the loss, right? Because you're finding a worst case scenario. If you maximize the loss, it would be just one point that maximize the loss, right? Maybe you have multiple points that have the same loss, but we're not considering that here. See? So, so once you find that point, you're going to just inject that point for epsilon n times because you are allowed to inject epsilon n poison. This is like, I'm reading Michael's note. This is like how in AdaBoost, the classifier player can just pick pure strategies. I'm not quite understanding this. Michael, do you want to?
I guess in the game theoretic version of it, they say that you have to weight a distribution over data points, but you can just pick one single classifier at a time because the inner part of the min and max, that always works. Is this the same thing?
Actually, that's not, but now I see what you mean by the pure strategy. That's not. What we're saying here is even simpler, right? So we wanted to make sure that we upper bound the worst scenario, okay? So what is the worst scenario? The worst scenario that, the points would make my loss bad, maximize my loss, essentially, right? So then that's why I'm saying I can find, so the goal is to find epsilon n points that maximize the loss. So let's say for, so let me put it this way. So you're allowed to find epsilon n points. Okay, this is what's allowed. Now I'm gonna call them x1, just for abuse of notation. I'm gonna call them x1 through x epsilon n. Okay, so also correspondingly, each of them would induce like a loss. Okay, I would induce a loss. Okay, so now I'm just saying that your goal is to make sure that the summation of is maximized. Okay, does that make sense? So if you want to maximize that, also you have to make it sure that all the xi's, yi's are within your feasible set, right? For this maximization, you have to satisfy this condition. Okay, so now I'm just asking, if you wanted to do that, basically, as long as you pick all the points to be the one that maximize the loss, you get the worst scenario. And that's why they say this is realized by a single point, xy was in F. Okay, that's even simpler, right? So can I get a feedback on whether people are following this? Okay, give me a thumbs up if that's fine. Okay, wonderful. I see a lot of thumbs up. Great. Okay, awesome. Okay, so this is basically what we wanted to say about the fixed defense. And again, I'm not talking about anything related to the property of the loss, right? The loss could be convex or non-convex until now, right? Because nothing has used the property of the loss function yet. However, what's nice about this is that when the loss is actually convex, the paper would give like an interesting result. I'll talk about it later, but let's look at the algorithm one. Algorithm one is what we've been talking about, the online learning algorithm for generating upper bound and candidate attack. So this is how they were doing it. Essentially, they were first calculating the xt, yt that maximize the loss, as you can see here. Oh, sorry. So as you can see here, this is how you're doing it, but we're doing it online. So, we're doing it for t examples, t from 1 to epsilon n. Now, once you get this xt, yt, what you do is you're going to get this u star. What is u star? Star is just the minimization of this term multiplied with this epsilon l, this term, the loss of this term, right? This is related to your u star before. Then you will do an update, find the gradient with respect to this loss function. And then you will update your z, and essentially you will update your lambda, and using the lambda and z, you would update your theta. Okay, so this, I don't want to go into too much details here, but so, the idea is that you are just going to find the maximization. So what I'm in the box is the most important thing I wanted to emphasize here. So you want to find the argmax that maximize the loss for the current step, although everything is in an online manner. Okay, so that's how you would find the upper bound as well as the candidate attack. Okay, so like I said, this algorithm, I don't want to go into too much detail, but more importantly, I think this polarization is also very interesting, although I don't plan to go through all the details. I just wanted to say the high level idea here is that if you do have an L, which is convex, then algorithm one would have some nice property in terms of the regret. So they would say that, so like saying here, suppose that the learning algorithm has regret t after t time steps, then for the attacker, the corresponding parameter theta tilde satisfy this condition. So what is this condition saying? It's just saying that this quantity here, the u would be an upper bound, u star would be an upper bound of m. That's of course very clear to us, even if it is not convex, still holds. But also, the u star and this term would not be deviated a lot, right? It's the difference is going to be upper bounded by the regret divided by epsilon. Oh, okay. Yeah, I didn't finish talking about this paper, unfortunately. Well, I hope we can. So let's see what's left. So I have only 2 more slides left, actually, but I guess it's not fair to take your time. So let's continue next time. Okay. Thanks, everyone.
Thank you.
Thanks.
Thank you.